Okay, so in this short video, I will talk about the link theorem. So let's first talk a little bit about the Hodge filtration. So consider X to be any smooth algebraic variety, and recall that as a consequence of the Hodge theorem, we have defined the algebraic Durand cohomology as follows. So the algebraic Durand cohomology is defined as the hypercohomology with coefficients in the complex of algebraic forms, and we know that this, in the case of a smooth algebraic variety, is isomorphic to the usual Durand cohomology. So in the case where X is smooth and projective, we define the Hodge filtration as follows. So we can define it in terms of the algebraic Durand cohomology given by the image of the hypercohomology group of the truncated complex of algebraic forms inside the usual hypercohomology of the complete complex of algebraic forms. So for example, this filtration will coincide with the usual Hodge filtration in the case of a compact Kähler manifold. But in general, this definition is not the good one. For instance, when we consider X to be an affine variety, we see that the hypercohomology groups of these truncated complexes are in fact the cohomology of global sections of this truncated complex. This is because we're in an affine variety, and so this complex is acyclic. So since we know by the Hodge theorem that the cohomology of global sections or global algebraic forms is the usual Durand cohomology in the case of an affine variety, this will correspond to the whole Durand cohomology group for every p less than k. So we will have that this filtration is in fact trivial. We are always taking the whole Durand cohomology group in the case of an affine variety. So in order to fix this problem of the definition of the whole filtration, the link noticed that the right chief to consider was not the chief of algebraic forms, but a subchief of it, which correspond to the chief of logarithmic forms. So let's introduce these forms as follows. So again, consider X to be a smooth projective variety and let Y to be an hypersurface. So we define the chief of logarithmic forms with poles along Y as follows. So we denote it like this, omega px log Y, and they will correspond to this kernel. So this is exactly the space of metamorphic forms with simple pole along Y, such that their differential also has simple pole along Y. So these logarithmic forms, they have a simple description in terms of charts in the analytic topology. So this is explained by the following proposition. So consider X to be a smooth projective variety of dimension n. Consider Y to be a smooth hypersurface. So we will explain this just in the case where Y is a smooth hypersurface. And let C1 up to Cn be local coordinates on an analytic neighborhood of X, such that in this chart, Y looks like the zero set of the first coordinate. Then, this chief of logarithmic forms, when it is restricted to this chart, it can be identified with the chief generated by the holomorphic forms, so the chief generated by these p forms, and also we can include meromorphic forms with pole along y, so along C1, but the pole always has to be of this logarithmic format. So it has to be of the form dC1 over C1, which some holomorphic form. So an example of logarithmic form is the following. So take x to be C2. Well, here we define everything for a smooth projective variety, but this proposition gives us a local description of the logarithmic form. So we would just give an example locally. So assume that maybe we're in P2, but we're restricting to this open chart given by C2. Let y to be a smooth plane curve of degree d positive, I mean bigger than 1, non-linear. Then this form, df over f, it is an example of a one form with logarithmic poles along y. But if we take dx over f, this is not anymore a logarithmic form, because when we differentiate this form, it will be meromorphic with pole of order 2 along y. Okay, before going to the proof of the link theorem, we will see the statement of a lemma due to Carson and Griffiths, and which will be used for the proof of the link theorem. So let's first introduce a new object. So consider x to be any smooth projective variety, consider y to be a hypersurface given by intersecting x with the hypersurface given by an equation f equal to 0 for some homogeneous polynomial in the ambient projective space. So let now U to be the Jacobian covering of X, which will be given by the intersection of X with the usual Jacobian covering of this hypersurface F. So we're assuming that F is smooth. Well, at least restricted to X. And these Fi's are the, as I said, well, it is the Jacobian covering, so Fi will represent the partial derivative of f with respect to the variable xi. For every number L bigger or equal than 2, we define this operator HL, which will take Q check cochains of the chief of P forms of order at most, with poles of order at most L along Y, to the space of Q cochains of the chief of P minus 1 forms with pole of order at most L minus 1 along Y. So this is an operator which reduces the pole order by 1 and also reduces the order of the differential form by 1. And it is defined in the following way. So, well, here is the formula. There is this constant term. We make this product by f over f j0. This is the term that reduces the pole order by 1. And we have also a contraction operator on this meromorphic form, which will reduce the degree of the form by 1. So Carson-Griffiths lemma says that whenever we look at the induced map by this operator in hypercohomology, we will get that this operator here, the usual differential in hypercohomology composed with H plus H composed with the usual differential operator in hypercohomology will be a map such that it will take, well, when considered on these quotients, it's the identity map. So in other words, we're saying that if we take some element in which is a representative in hypercohomology, and we apply this operator to it, so since it is a representative in hypercohomology, d of this element will be 0, so this part will vanish. And on the other side, we will get d applied to h of omega, right? And so this is saying that our term omega minus dh omega, which is an exact term, will be 0 in this quotient, right? And being 0 in this quotient is the same as saying that the representative has all its terms with a pole of order 1 less, right? In other words, we're saying that whenever we apply this operator, the identity minus dh, to any representative in hypercohomology, we will get another representative with a reduced pole order in 1 degree. Okay, so let's state now the link theorem. Consider X to be a smooth projective variety, Y to be a smooth hyperplane section, and consider U to be the complement of this hyperplane section inside X. So in general, we can also state the link theorem for any affine variety. So if we want to consider an affine variety as a difference of a smooth projective variety and an hypersurface, the best that we can assume is that this hypersurface is not a smooth hyperplane section, but a normal closing divisor inside X. But the proof that we will give here uses Carson-Griffiths lemma, and for this we need to restrict ourselves to this other context. So the link theorem is stated as follows. So consider U inside the projective variety X, and then the natural map that takes forms with logarithmic poles inside forms of arbitrary pole order, which is the same as the space of forms, algebraic forms defined over U. Then this map, this morphism of sheaves, is in fact a quasi-isomorphism, and so it induces isomorphisms in hypercohomology, right? And this theorem is the one that is telling us that in the case of an affine variety, instead of computing the RAM cohomology in terms of the hypercohomology of the sheaf of algebraic forms on U, we can compute the same group in terms of the hypercohomology of this sheaf of logarithmic forms along Y. And so, using this other way to define the algebraic RAM cohomology, we define the Hodge filtration in the case of an affine variety by letting the filtration to be given by the image of the hypercohomology of the truncated complex of forms with logarithmic poles inside this algebraic RAM cohomology of U. So it turns out that this filtration is the good Hodge filtration in the case of affine varieties, and moreover, we will see later in Griffiths-Bessey theorem that this kind of filtration behaves well under the residue map. So finally, let's give the sketch of the proof of the link theorem. So we will just show that this morphism of hypercohomology groups is an isomorphism. So let's call that morphism phi. And let's start by showing that it is surjective, right? So what does that mean? This means that whenever we have any representative here in hypercohomology where the terms in the representative are of pole of arbitrary order, then we have to show that we can always reduce the pole order until making each term a term with logarithmic poles along y, right? So take any representative with poles of arbitrary order along y, and then we know that applying Carson-Griffiths lemma, we can use this operator identity minus dh to obtain another representative where the pole order has decreased by 1 in each term. And so if we apply this operator enough number of times, we will get a representative with poles of order 1 along y. So using that this representative is also declosed, it's not too hard to show that then all the elements in this representative has to be forms with logarithmic poles. So this is how you prove the surjectivity. And for the injectivity, assume that we have a representative here in this hypercohomology group. So it is given by forms with poles, with logarithmic poles along y, such that it is 0 in this other hypercohomology group. So this means that there exists some form with poles of arbitrary order such that omega is d of eta. So again, by Carson-Griffiths lemma, we can replace this eta by something of poles of less order, right? So we can take eta tile to be 1 minus dh applied enough times in such a way that this becomes a representative where all the terms have pole of order at most 1 along y. It is easy to see that the d of eta tile is the same as d of eta, and so we can also write omega as d of eta tile. And similarly to the surjectivity case, we can also see without too much effort that since omega has logarithmic poles along y, then this eta tile, since it is satisfying this relation, also has to have poles, logarithmic poles in each of its terms. And so this completes the sketch of the proof of the link theorem using Carson-Griffiths lemma. In this short video, I will talk about Griffiths-Bessey theorem. So let's start recalling what is the residue map. Consider y to be a smooth projective variety of dimension n plus 1, and x to be a smooth hypersurface inside y. Let C1 until Cn plus 1 be a chart on y, defined on an analytic neighborhood of y, in such a way that in this neighborhood, x corresponds to the 0 locus of the first coordinate. Then, The residue map is a morphism of sheaves which can be defined in these small open sets as follows. So it will go from the sheaf of logarithmic forms with poles along x to the sheaf of p-1 forms on the hypersurface x. So we know that an element of this sheaf in a chart like this is always possible to write it in the following format. So it can be a holomorphic form plus another holomorphic p-1 form, wedge the logarithmic form dc1 over c1. Then the residue map will be the map that takes this part of this form, beta, and restrict it to the hypersurface. So as I said, beta and gamma are holomorphic on B, and it is an exercise to see that this map is in fact well defined. It is a morphism of sheaves and is independent of the choices that we have made. Moreover, this morphism of sheaves is surjective, and it has kernel the space of p-forms along on the smooth projective variety y. Hence, we have this short exact sequence of sheaves called the Poincare residue sequence. Moreover, it's not hard to see that this sequence is compatible with the usual exterior differentials on each of these sheaves, and so it is a short exact sequence of complexes of sheaves. Then, in particular, we can see the residue map as a morphism of complexes of sheaves, and so it induces a morphism in the hypercohomology groups. This is a residue map in hypercohomology, but we know that the hypercohomology groups of the usual forms with logarithmic poles by the link theorem correspond exactly to the hypercohomology of the complement of the hypersurface in Y. On the other hand, we know by Atiyah-Hodge theorem that the hypercohomology of the usual algebraic forms on X is nothing else than the RAM cohomology of X. So this map in hypercohomology, since it comes from this other map of complexes of sheaves, which lies inside a short exact sequence of complexes of sheaves, this is part of a long exact sequence in hypercohomology that once we identify each hypercohomology group with the corresponding RAM cohomology group, corresponds to the classical Leray-Thom-Geising sequence, which is given as follows. In the particular case where Y, the ambient space, is the projective space, and X is a smooth hypersurface of the projective space, looking at this Leray-Thom-Geising sequence and recalling that the RAM cohomology of the projective space in primitive cohomology is always 0, we see that this residue map is in fact an isomorphism between the complement of the hypersurface and the primitive part of the hypersurface. So let us state now Griffith's basis theorem. So we consider X to be a smooth hypersurface of dimension n inside Pn plus 1 and of degree d. So Griffith's basis theorem tells us how to construct a basis of the RAM cohomology of the middle RAM cohomology group of X, and moreover, this basis is compatible with the Hodge filtration. So in order to state the theorem, we will divide it into two parts. So the first Griffith theorem is the following. So it says that when we consider the following map, which is induced by the residue map, this map takes a polynomial of degree d times q plus 1 minus n minus 2 and gives us the residue of the meromorphic form induced by this polynomial. So this form will be p times the standard top form of degree n plus 2 over f to the q plus 1. So it is a meromorphic form with pole along x of order q plus 1. So we know that these forms, they always belong to the primitive part of the middle, the RAM cohomology group of X. But what the theorem is claiming is that this always lands in the n minus q part of the Hodge filtration of this group. And moreover, this is surjective. The second Griffiths theorem says the following. So once we consider the above map and we compose it with the canonical projection to the quotient of the Hodge filtration with the next piece of the Hodge filtration, like this, then we obtain a map which is again surjective, and the kernel of this map is the Jacobian ideal. And so, in consequence, we obtain an identification of this homogeneous piece of the Jacobian ring with the n minus q part of the Hodge decomposition in primitive cohomology. So, before proving Griffiths' basis theorem, let's recall some preliminaries. The first preliminary is the Vought vanishing theorem, which is as follows. Consider X to be any hypersurface, and then we know that several cohomology groups of the sheaf of differential forms with poles along X vanish. In fact, this happens for any order of the pole, for any degree of the form, and for q bigger than 0. A corollary of Vought vanishing is the following. We can, in fact, describe explicitly how are all global sections of n-1 forms of any degree. So the description is as follows. They are always combinations of the contractions of the standard top form in Pn, contracted by the coordinates of the ambient space Pn, times some polynomial of the right degree, right? In this case, the degree is L minus N. So this is how all these global twisted n-1 forms look like. The final preliminary is Carson-Griffiths lemma, which we have already seen it in the previous video, but we will state it now in a simplified version. So consider X to be a smooth hypersurface, let U to be an affine upper covering of Pn, fix some number L, and fix some representative in hypercohomology omega, starting from omega k until omega n, where each omega I is a cochain of the space of I forms with poles of order at most L along X. And then we know that there exists this operator H, such that when we apply the identity minus dH to omega, we are able to find another representative in hypercohomology, probably with one extra term, but it is such that all these terms have poles of order at most L minus 1 along X. So this operator provides us with a method to reduce the pole order of the representatives in hypercohomology. Okay, so let's start with the proof of Griffiths theorem 1. So Recall that we want to show that the image of the map induced by the residue map lands in some piece of the Hodge filtration of this group here. On the other hand, we already note that the residue map gives us an isomorphism between these two groups, and moreover, this isomorphism is an isomorphism of Hodge structures. And so we know that the Hodge filtration of this side will correspond to some Hodge filtration in the RAM homology of this affine variety. Then, what the theorem is claiming is in fact that this part of the Hodge filtration in the affine variety correspond exactly to these representatives. So let us prove this claim. So by definition, we know that the Hodge filtration of this homology of the affine variety is just the hypercohomology of the truncated complex of logarithmic forms. So if we take any representative here, in this part of the filtration, we know that since this is declosed, then this part of the representative must be closed under the check differential. And so, using the Bott vanishing, we know that the higher cohomologies of the chief of n plus 1 minus q forms with poles of any order along x always vanish, right? And so since this term is delta closed, it has to be delta exact. Hence, we know the existence of this form eta such that this equality holds. Using this form eta, we can replace the representative omega in hypercohomology by omega minus d eta. Once we do this, we will cancel this first term of the representative, and so we will obtain another representative with one term less, but it's not hard to see that since we are adding or subtracting the differential of eta, the differential d of eta, this differential can possibly increase the pole order of this form here. And so this omega tilde n plus 2 minus q has pole of order at most 2. So we can iterate this process, and inductively we will obtain at the end only one term here, omega tilde n plus 1, which will correspond to a global form, but with pole of order at most q plus 1. So it will correspond exactly to a form of this format here. So this argument proves that the left-hand side is in fact contained in the right-hand side. So conversely, we want to show that the right-hand side is also contained in the left-hand side. So consider any meromorphic form here with pole of order at most q plus 1 along x. And then what we want to show is that when we look at this element in the hypercohomology, we can always reduce the pole order until making it of order 1. So using the Carson-Griffiths lemma, we know that applying this operator, we are exactly doing that. We are reducing the pole order by 1 each time that we apply it. But also we are increasing the size of the representative by adding one extra term. And so we know that once we apply this operator at most q times, we will land in a representative with logarithmic poles, and the size will also has to be of at most q plus 1 terms. So it will start always from this omega n plus 1 minus q, and so it will be an element of this part of the Hodge filtration. So this proves the first Griffiths theorem. So finally, let's prove the second part of Griffiths theorem. So for the second part, we have to show that this map, when it is composed with the quotient of the next piece of the Hodge filtration, so when it is looked module this subgroup here, we have to show that the kernel of this map is exactly the Jacobian ideal. So by the first part, this means exactly that being in the kernel is the same as claiming that this form belongs to the Fn plus 2 minus q part of the rank homology group. And we know that how are all the elements in this group. So this is possible if and only if there exists another polynomial q of a smaller degree, b times q minus n minus 2, such that this meromorphic form is equal to this other meromorphic form with a smaller pole order. But this equality has to hold in the rank homology group. So by Atiyah-Hodge theorem, we know that the rank homology group of this variety, which is an affine variety, can in fact be computed in terms of global sections. And so, since both are global sections, this equality is equivalent to saying that the difference is exactly the differential of a global section. And here, a global section means exactly this. It's a meromorphic form with poles along x of order at most q. So on the other hand, we know by the corollary of Roth vanishing that we can write explicitly how this omega should look like. And it turns out to be something like this. Once we replace this expression in the above equality, we will see that the condition of P being in the kernel, this means that there exists some Q and some omega, or maybe some TIs, such that the equality holds, is equivalent to having the following relation, which claims that this meromorphic form is in fact congruent to this part, which appears once you differentiate this expression here, module some meromorphic form with pole of order at most q along x, right? And this kind of equality can be translated into a purely congruence in terms of polynomials, because here we can clean f to the q plus 1, we can also clean the term omega, and so we will have a congruence p congruence to minus q times the sum of ti's times fi, module the ideal generated by the polynomial f. And so, since f always belongs to the Jacobian ideal of f, we see that having this equality is equivalent to saying that P is in the Jacobian ideal. And this proves the second part of Griffiths' theorem and completes the proof of Griffiths' basis theorem.